In this video, I'll work through some sample problems on mathematical writing. When we think about mathematical writing, we talk about counterexamples a lot, so it's important to first understand how to find a counterexample for a false if-then statement. So the if-then statement follows this quantified clause. So we say, for every positive integer n and every positive integer m. That quantifier just sets the stage. That tells us the universe that we're living in. We're living in the universe where n and m are positive integers. The real meat of the statement comes after that. So it says if n is odd and m is even. So that's the hypothesis. The hypothesis is the if part. And it says then n plus m is divisible by 3. So that's the conclusion. And what we know is that an if-then statement is only false when the hypothesis is true and the conclusion is false. So if we're looking for a counterexample, what we're looking for is a value of m and a value of n where the hypothesis is true and the conclusion is false. If we can find that, then we have found a counterexample. So we're looking for n being odd and m being even. That's the hypothesis being true. And we're also looking for n plus m not divisible by 3. That's the conclusion being false. So now we're just going to experiment. We're going to play around and look for numbers and see if we can figure out whether we can find an n that's odd, an m that's even, and where n plus m is not divisible by 3. And we might not find it right away, but if we eventually find it, then we have found our counterexample. So the typical way that we start this is we start by picking things that make the hypothesis true, and then we check the conclusion. So we need an odd number for n and an even number for m. So how about n equals 5 and m equals 10? And again, if we check here, is n odd? Yes. Is m even? Yes. So that means the hypothesis is true. So now we'll check the conclusion. So n plus m, that's going to be 5 plus 10. Is that divisible by 3? Yes. It's 3 times 5. So that means that we didn't find a counterexample. We found a situation where the hypothesis is true and the conclusion is true, which in that situation shows us that the if-then statement is true. Now, that doesn't show us that the if-then statement is always true. Remember, the statement here says every positive integer n and every positive integer m. So not finding a counterexample, failing to find a counterexample, isn't a proof. It just means that we didn't find a counterexample. So since we're looking for a counterexample, we're going to try again. So what if we try n equals 7 and m equals 4? So is n odd? Yes, 7 is odd. Is 4 even? Is m even? Yes. So again, we're in a situation where the hypothesis is true, and again, we're going to check the conclusion. Well, this time, n plus m is 7 plus 4, which is 11, and that's not divisible by 3. And so that shows us our counterexample. We had n odd, m even, and n plus m not divisible by 3. So this is our counterexample. So to write a proof of an if-then statement, what we're doing is we're explaining why a counterexample cannot be found. Because remember, if you just try to find a counterexample and fail, that doesn't mean that you could never have found a counterexample. It just means that you didn't find one. And maybe if you had tried harder or thought differently, you might have found it. So a proof is a convincing argument that you should give up trying to find a counterexample, that you're never going to be able to do it. So the way a proof typically is written is we start by supposing that we have the hypothesis being true. Again, we're imagining that we're talking to someone who is in the process of trying to find a counterexample. And we say, okay, well, if you've picked something that makes the hypothesis true, I will explain to you, me being the person writing the proof, I will explain to you why the conclusion will have to be true in that situation. So the first sentence of our proof is going to be putting us in that situation where the hypothesis is true. In this case, the hypothesis is n is even. And so we're going to start our proof by saying let n be an even integer. And then at the bottom, our goal now of our proof is to prove that 3n has to be even. So at the bottom of our proof, we're going to leave some space. We're going to want to be able to say at the end, therefore 3n is even. That gives us our goal. That gives us what we're going to be working towards. Now back up to the top of the proof. What does it mean for n to be an even integer? Well, we have a definition of even. And we know that when n is even, that means n can be written in the form 2 times an integer. So we will say, so n equals 2a. You can use lots of different letters of the alphabet. I'm deciding to use the letter a. So n equals 2a for some integer a. Again, we're using variables here because, again, what we don't want to do is pick a specific even integer, right? We don't want to say, well, if n is 10, then 10 is 2 times 5, right? We want to be able to prove to the person trying to find counterexamples that it doesn't matter what number they pick. If they make the hypothesis true, the conclusion is going to have to be true. Okay, so how do we go from n equals 2a to thinking about 3n being even? Well, we have a formula for n, so let's plug that into the expression 3n. So we might say, now, what does 3n look like? Well, 3n looks like 3 times 2a, which is 6a, but I can rewrite that as 2 times 3a. Now, why am I doing that last step? Why am I writing it as 2 times 3a? I'm thinking about my goal. I know I want to show that 3n is even, and I know what it means to be even is that you can write that number as 2 times an integer. So my goal is to write 3n in that form, 2 times an integer. And now I've done that. Since a is an integer, 3a is an integer. There I'm using that closure property of the integers, that if I multiply 2 integers together, I get another integer. Since a is an integer, 3a is an integer, and so that means that 3n is even. So I reached my goal. I said that therefore 3n has to be even. So that's the basic structure of a proof. We start with a hypothesis, we use our definitions, and we work towards our conclusion. So here we have another similar if-then statement. This one involves 2 variables, but we're going to approach it in the same way. Again, our hypothesis in this case is m plus n is odd. That's our hypothesis. And our conclusion is m or n must be even. That's our conclusion. So if we start this proof in the same way, we can do it for a while, but you're going to see we're going to run into a problem. So we start with the hypothesis. We say let m and n be integers such that m plus n is odd. Now, we're not exactly sure what to put as our conclusion, right, because we need to prove that m or n is even, so we're not really sure if we're going to be proving that m is even or whether we're going to be proving that n is even. So that's a little bit, we're not sure what to do at the end there. But let's keep proceeding from the beginning here. We know m plus n is odd, okay, so that means that m plus n is equal to 2b plus 1. I'm using the letter b because I used the letter a in the previous proof, so just for variety. So m plus n equals 2b plus 1 for some integer b. But now I'm kind of stuck, right? Because I've got this equation involving m and n, but it's involving both m and n, and I don't know how to sort of rip it apart so that I get an equation that only has m in it or only has n in it. So I'm not exactly sure how to proceed at this point. So we're kind of stuck. So now what we're going to do is think of this proof in a different way. So we're starting all over again. And as we sometimes do, we're going to think of this hypothesis, we're going to call that P, and our conclusion, we're going to call that Q. So this if-then statement can be written in symbolic notation as P implies Q. But as we've learned, the contrapositive has the form not Q implies not P, which in this case would be the statement, well, what's the negation of m or n must be even? Well, remember, we have De Morgan's laws, and one of De Morgan's laws says that if you negate an or, you get an and. So if I have not r or s, that's the same as not or and not s. So the negation of m or n must be even is that m and n must be odd. So that's the hypothesis of my contrapositive. So we want to, just because of English, put this in more natural wording. So we'll say if m and n, well, we wouldn't say must be there just because of English rules. We would say are. So if m and n are odd, and then our conclusion, our new conclusion, is not P. So we would say then m plus n is even. So that's what we're now trying to prove. We're trying to prove if m and n are odd, then m plus n is even. Now that we've got our new equivalent if-then statement, we're going to prove it in a very similar way. We're going to start by saying let. Now our hypothesis says that m and n are both odd. So we'll say let m and n be odd integers. Now we've got two facts here. The two facts are that m is odd and n is odd. So we have two uses of our definition of the word odd. So m equals 2c plus 1 and n equals 2d plus 1 for some integers c and d. Remember, as far as we know, m and n might be different numbers, and so we need to use different letters, c and d here. So now our conclusion is that m plus n is even. So we should look at what m plus n actually looks like. So now m plus n is going to be 2c plus 1 plus 2d plus 1. So that's going to be 2c plus 2d plus 2. Remember, our goal is for this to be even, which means we want to be able to write it as 2 times an integer. And so we can factor out a 2 here. We've got 2 times c plus d plus 1. C plus d plus 1 is an integer. And that shows us that m plus n is even, just like we wanted. And there's our conclusion. So as we see here, sometimes we need to look at the contrapositive. It ends up being a little bit easier to write the proof that way. Now, sometimes you'll be told to do that, and sometimes you'll just have to kind of figure that out on your own. So learning to write good proofs takes time, it takes practice, so keep working at it. Look at the proofs that I've worked through in this video and the practice problems that we've done in class and in your assignments, and keep working on it.